Hello and welcome to our lesson on radical functions. So we've talked about the parent, radical, square root and cube root functions in our first module on functions, but we want to go a little more in depth here and talk about specifically the domain for these radical functions. And so just to recap, let's take a look at our parent square root and parent cube root functions and talk about some characteristics. So radical functions with even roots, square roots, fourth roots, sixth roots, they're all going to behave the same way because they have similar restrictions. So again, just to recap, let's look at our parent square root function, which is y equals the square root of x. I know we have technology that graphs for us, but let's make a table just again to get a full understanding of what's happening here. Usually when we're making a table of values, we can pick whatever we want for x, we plug it in, it produces a y, and we plot the points. But we don't have that happening here. I can't put whatever I want in there for x. In fact, there is a starting number. There is a smallest number that I could put in, and then anything after that's going to be fine. But what is the smallest number we could put in for x? Smallest number we can square root is going to be 0. Nothing negative is defined underneath the square root, and that's true for the fourth root, the sixth root, any even root. We can't take even roots of negatives. The smallest number we can take the even root of is 0, and in this case the square root of 0 is going to be 0. And then I could square root 1 and get 1, and I could square root 2 and get a decimal, but I don't want to graph that, so I'm going to skip to the next perfect square, which is 4, where the square root of 4 is 2. And then again, I'm going to skip all the way to 9 because the square root of 9 is a nice 3. So we're going to have a point at 0, 0, a point at 1, 1, at 4, 2, at 9, 3, and this graph's just going to keep going. So it's going to keep going in this direction with this little sort of hill-shaped graph, but it won't continue. So it'll continue forever going to the right, but there's going to be this end point on the left. This graph is going to start at that point and then continue in only the one direction. So we have a restriction here, and it will be the same for all even roots that are all radical functions with even roots are going to have restricted domains and restricted graphs, or the graphs are restricted to specific domains. There's going to be some starting point, and then the graph will continue only in one direction. And that's because, again, we can't take even roots of negatives. So there are a bunch of x's that have to be excluded because they might make the radicand a negative. And then, of course, we know transformation rules. Those still apply. So our domain for this particular graph, or this particular function, or we can see it in the table of values, the domain of the x values that apply here would start at 0 and go forever. So this domain is everything from 0 to infinity, right? Now that could change because we could shift our graph around or we could reflect it, but you're going to have some starting point and then you'll go forever in only one direction. All right? So that's our even root concept. Again, all even roots are going to behave the same way. In fact, let me just show you here. If I put in the square root of x, which we just saw, square root of x, there's our graph. If we put in the fourth root of x, let's get our fourth root in here, you're going to see basically the same behavior. Okay, it's the blue one. It's a little bit compressed, but the same effect is happening. And if I put in the sixth root of x, let's make it the sixth root of x. Again, the same behavior, where it's the green one now, where you have that starting point and you continue forever in the one direction. It's a little more compressed, but same behavior. All even roots are going to have a starting point, and then you'll go forever in one direction. Now again, you could flip this around. You put a negative. Well, that won't change the domain, but if you put a negative, let's say in here, then you could go forever to the left instead of going forever to the right. And again, you could shift it up, down, left, right, but all the radical functions with even roots will behave the same way. And then the same for odd roots. So let's talk about the parent cube root function, because it's going to pretty much show us how all of our odd root functions behave. We don't have the same restrictions with the cube root or odd roots that we do with evens. So I could cube root, let's say a -8 and get a -2. or cube root a -1 and get a -1, or cube root 0 and get 0, or cube root 1 and get 1, or cube root 8 and get 2. So remember, the cube roots of negatives were negative, the cube root of positives were positives. So what we have on this graph is something similar on the right side of the graph. So we have this point at 0, 0, at 1, 1, at 8, 2, right? This part of the graph looks pretty similar, which makes sense. It is a radical function, but instead of being restricted and having that starting point, then we can also extend to this other side of the graph. So we have two pieces here that are going forever in both directions, where the cube root of positive numbers are going to be positive results. So when you put in a positive under the radical, you get a positive back out for the result. So we see this graph that's in the first quadrant. And then instead of being restricted, because the cube roots of negative numbers are going to be negative, then you see this other part of the graph that is in quadrant 3, right, where negative x's produce negative y's. So that's going to be true, again, for all odd root functions. Any radical function that has an odd root, again, that means an odd index, it's going to have an unrestricted domain, an unrestricted graph, a graph that's going to go left and right forever, which means the domain is everything from negative infinity to infinity. And even though the transformation rules apply, it doesn't matter if I shift this graph up, down, left, right. If I reflect it, it's still going to go left and right forever. So the domain will always be, we can say, all real numbers, or everything from negative infinity to infinity. And again, just so I can show you, if we made this the cube root, there's our cube root function. If I made this the fifth root, okay, it's a little bit compressed, but the behavior is the same. And if I made it a seventh root, okay, again, a little more compressed, but the same behavior. So all odd roots will behave the same way. Okay, so whether we wanted to look at the graph or not, just knowing what we know about these radical functions, we should be able to find our domains or identify our domains with just a little bit of work. So if you're asked to find the domain for a radical function without graphing, odd roots are simple. Okay, if it's an odd root, you just have to recognize that it's an odd root and remember that there are no restrictions. No restrictions for odd roots. Our domain always will be negative infinity to infinity, or all real numbers. So if you see a cube root, a fifth root, a seventh root, any odd root, just remember, no restrictions for odd roots, no restrictions on the domain. Now, if it's an even root, there are going to be restrictions. And based on where the graph goes, the restriction could change. It could be that it starts at 0 and goes right forever, or it could start at 0 and go left forever, or it could start at 2 or 3 or -2 or -5 and go left or right forever. So how do we determine where our graph's going to go? Well, we could actually look at the graph, right? We have Desmos, put the graph in, or put the function into Desmos and look at the graph, or know that our radicand, that is the part underneath the radical, has to be at least 0. So if we make our radicand at least 0, mathematically we could say at least 0 as greater than or equal to 0. Then we can actually solve and figure out where our x's begin or end. Okay, so I wanted to put this in two separate lines. Our radicand has to be at least 0. So at least 0 mathematically is going to be greater than or equal to 0. And if we solve that inequality, we're going to figure out the restrictions for x. And again, we could always use Desmos to graph and picture it that way. That's totally fine to verify, or even just to start there. So first one, now again, there's a couple ways to do this. I can look at the graph, but hopefully we know what this graph's going to do. Okay, what does that +4 do to the graph? If that +4 is going to make this graph go to the left 1, 2, 3, 4, then I can already see my domain is going to go from -4 to positive infinity. So if you can visualize that in your head, awesome. If you want to put it in Desmos, we're going to see the same thing happen. If we put in y equals the square root of x plus 4, then you see it again, -4 to positive infinity is our domain. Or, I know, if I want to do some algebra here, I know mathematically that my radicand has to be at least 0. So if I take this x plus 4, the radicand, and say it has to be greater than or equal to 0 and solve, I can also find my domain. So solving this is just like solving an equation. I'm going to subtract the 4 over and say that, well, x has to be greater than or equal to -4. So that would be one way to state the domain. We could say our domain is, I have space. Let me say this domain could be all x's such that these x's are greater than or equal to -4. Or we could say this domain is everything from -4 to positive infinity. Okay, so either one of those would be acceptable ways to state that domain. So we've got options again, fourth root, and then now we're flipping over the y-axis, and we're going to be shifting. So if you want to look at Desmos or picture that in your head, that'll work. Otherwise, the fourth root is restricted. We want to make sure this radicand 2 minus x is at least 0. So when we solve this, we would subtract 2, and that would mean a negative x is greater than or equal to a -2. And then we have to divide both sides by the -1 that's in front. And so that gives us x. And then we have to flip our inequality symbol, and then we have a 2. I don't know if you remember that rule, but you have to flip your symbol if you're dividing by a negative number. And why do we have to do that? Well, it has to do with the domain and the transformation that or the impact that negative has in terms of transformations. So if this was a fourth root, y equals fourth root of, let's say, 2 plus x. Okay, if that negative wasn't in there, then we're just shifting over 2, and we could see just like a square root, right? We're just shifted over 2, we're going to go from -2 to infinity. But the negative in front of the x reflects it over the x-axis, or sorry, over the y-axis. So if we reflect it over the y-axis, we change directions on the graph, then we're no longer starting and going right forever. This time we are going left forever, and then we have an endpoint, a stop point. So the reason we flip the inequality when we solve is because the negative in front of the x, it's not just one of these rules like, oh, divide by negative, flip the symbol. It's because that negative in front of the x flips the graph. Okay, it makes all the x's that were before that starting point the valid x's instead of the ones after. So we flip the inequality symbol to make sure that we're capturing the correct domain. All right, that's why that rule is in place if you never knew. All right, so all x's less than 2 are in our domain. So we could say this domain is all x's such that these x's are less than or equal to 2. Or we could say everything from -infinity up to 2 is in our domain. Okay, so either one of those would be acceptable answers. And alright, next guy, a sixth root. So we haven't seen anything outside of the radical yet, but what does a number outside of the radical do? What is this -3 going to do to our graph? Okay, let's look at an example. And I'm just going to put a square root. Let's go ahead and put a sixth root. It's the same behavior as the square root, but just so you're like, what the heck? So here's our parent sixth root function. Looks just like the square root. If we put a negative out in front, then it reflects over the x-axis, but does it change the domain? Well, no, we still start at 0 and we still go right forever. If I put a 3 out there, then it vertically stretches the graph, but does it change the domain? No, it still starts at 0 and goes right forever. So even though we have this extra piece here, this extra piece stretches our graph. It's a vertical stretch. A vertical stretch. And a reflection over the x-axis. Even though those two transformations happen, neither one of them affects the domain. Reflecting over the x and stretching it out didn't change the start point or which direction the graph went. So that -3 has no impact on our domain. All we need to worry about is the radicand. We just need to make sure the radicand, the x minus 5, is at least 0. So we are still just solving using the radicand, so we know x has to be greater than or equal to 5. And again, we saw that in the graph. So we're going to say that this domain could be all x's such that those x's are greater than or equal to 5, or we're going to say this domain starts at 5 and goes forever toward positive infinity. So either one of those would be fine. Okay? Here's one for you to try. One for you to try. Again, this graph has a plus 5 at the end. What is the effect of the plus 5 at the end? Well, that's going to shift the graph up 5 units. If I take a graph, if I take my square root of x, and then I just shift it up 5 units, is that going to affect the domain? Nope, still starts at an x value of 0 and goes right forever. So again, we can ignore that plus 5. It doesn't affect the domain. Doesn't impact the domain. And I should have put that over here as well. Vertical stretch from function of the x-axis. This doesn't impact the domain. Okay, so same thing here. I just need to make sure that my radicand, my 2x minus 6, is at least 0. So if I add 6 to both sides, then I know that 2x has to be at least 6. And if I divide both sides by 2, then I know x has to be at least 3. So these x values have to be greater than or equal to 3. So we're going to say this domain is all x's such that our x's are greater than or equal to 3. Or we could say this domain starts at 3 and goes forever toward positive infinity. Okay? And what do we got here? This is best case scenario, a cube root. So here you just have to recognize that this is an odd root. Odd roots do not have restrictions. You can take an odd root of any kind of number. Positive, negative, 0, decimal, it doesn't matter. It will work. So recognizing that is an odd root automatically tells you that this is unrestricted. This domain is everything from negative infinity to infinity, or we could say it's the set of all real numbers. And then the same thing here. Doesn't matter what's in this function. If it's a fifth root, it's going to go left and right forever. So this domain is all real numbers, everything from negative infinity to infinity, or the set of all real numbers included. And again, if you weren't sure, put it into Desmos. You're going to see, let's see, the fifth root of x plus 3, and then after a minus 4. Whatever happens to our graph, it's going to go left and right forever because it's a fifth root and it's unrestricted. Okay? So there's that. Now we have one question here, and you're going to see something similar to this in practice, probably a quiz too. Select all statements that are true of the radical function that is graphed. And there should have been an arrow here that I forgot to add into my graph. Okay, so it says the graph represents a radical function with an even root. That's going to be true, and I know that because there's an endpoint on that graph and we go forever in one direction. If it was an odd root, then you would see a graph that went forever in both directions. So that has to be true. It has to be an even root. It says the equation for the function could be a fourth root of x plus 3 and minus 2. So fourth root, we've established even root's good. A plus 3 and a minus 2, this would make our graph, instead of starting at the origin, it would go to the left 3 and it would go down 2. So this one would start here. The original starts here. If I went left 3, well, there's no markings here, but 1, 2, 3, and down 1, 2, then I would start there instead. So the starting point looks good. So that checks out, that checks out. However, if I just shifted left 3 down 2, then my graph would look like this. And this graph is upside down. And so this could not be the function because this graph is reflected. This is reflected over the x-axis. It's upside down. So this one is going to be false because it should have a negative right there. A negative would make that true. Okay, so, oops, dropped my pen. Let's go, this was good, and then this was left 3, down 2, so that was good, that was good. But it should have had a negative. It's missing a negative right there. Okay, if you put a negative right there, then it would have been perfect. And again, if you just put that function that I just wrote stuff all over into Desmos, you're going to see that the graph doesn't match the one that's on the paper. Okay, next one says the domain is from -3 to infinity. -3 to infinity, that looks good for the domain. So we're going to say yes, that one's true. The range is -2 to -infinity. Is close-ish. So the range does have an endpoint here at -2, and then it does go down to -infinity, but when we're giving this, it's supposed to go smaller number to larger number, so this is going to be wrong because it should be from -infinity up to -2. Okay? So otherwise that would have been fine. The function is decreasing over its entire domain. Decreasing. If we follow this left to right, it's going to continually be going down. Yes. So we're going to circle that one is true. And then the last one, it's negative over its entire domain. Negative means below the x-axis. No matter what, is this graph going to be below the x-axis? Well, if it starts here and goes down forever, then yeah, it's going to be below the x-axis the entire time. So we're going to select true for that one as well. So this is going down left to right. Left to right, and this one is below the x-axis. And that's true. Okay, so there it is. Hopefully not too much for this particular lesson. You'll have some practice to try out, and as always, if you need some extra help, then just reach out. Alright guys, take care.